Hello Internet. Today I will go over insertion sort. First of all, I will go over the code, but please don't be put off. I'll go over the code and then we will have a look at an example, and then I will go over the example in a bit more detail and hopefully it will be a lot clearer to you. Insertion sort. This has passes of n-1, which means that the list will be decreasing by 1 each time. This is the search list that will be decreasing. The comparisons that will be made will also be n-1, because each time we go through the list, we make one less comparison. Its complexity, however, is still n squared. The number of swaps in the worst case scenario will be 1 swap per pass. If we look at the beginning of the code, it starts off at 1 because it assumes that 0 is already sorted and goes on for the length of the list. We have a couple of variables that are set, and within the for loop is a nested while loop. While the position is greater than 0 and the list position that is adjacent to it is greater than the current value, the following code will run. The position equals the position adjacent to it, so it shuffles along 1, which then creates an empty space which the current value can be inserted into. This may seem a little complicated, so let's get on with the example. The algorithm starts by assuming what's in index 0 is in the sorted portion of the list, and I'm going to indicate that by using this ruler. Now, we move along 1. And we look at 23. 23 is greater than 16, so that stays where it is, and the sorted portion extends to create these two. We then look at 45. 45 is greater than 23, so the sorted portion again extends by 1. We look at 1 and compare that to 45. That's great, that's less than 45, so 45 then shuffles along 1. We then compare 23 to 1. 23 is greater than 1, so 23 shuffles along 1. We then compare 16 to 1. 16 is greater than 1, so 16 shuffles along 1, and we insert 1 into the empty space. And our sorted portion moves up 1. We then look at 3. It's good to bear in mind that 3 is going into a variable, like a temp variable. That's why it's not directly swapping with 45. 45 will be moving into where 3 was. So 45 is greater than 3, so it moves to the empty space. 23 is greater than 3, so it moves to the empty space. 16 is greater than 3, so it moves to the empty space. 1 is less than 3, so 3 is inserted into the empty space. And our sorted portion is extended again. Then we look at 10, and we compare that to 45. 45 is greater, so it goes into the empty space. 23 is greater than 10, so it goes into the empty space. 16 is greater than 10, so it goes into the empty space. 3 is less than 10, so 10 is inserted into the empty space. And our algorithm is complete. Before we look at what's going on in the algorithm, let's just check out what happens when we have a swap. So you have some items in a list, and you want to swap this one with this one. This one here goes off to a temp. This one here then moves into this position, so your list then looks like that. Then this one is then copied into this position, so your list ends up looking like this. So that's what happens in a swap. Right, with that in mind, let's check out an example list. So in this list here, let's make it a bit longer. In this list here, the unsorted portion is everything this side. The sorted portion, I'm sorry, the sorted portion is everything that side. The unsorted portion is this side. This guy here, we're going to assume is already sorted. And we're going to take the first element in the unsorted portion and then compare it here. Well, there's not much room to maneuver here. And the calculation is that 4 is greater than 5. No, it's not. So it's going to move over. And our swap occurs. So this goes off to the temp box. This guy is copied over to here. So we end up with and then whatever is in the temp box then gets copied into here, so we end up with this list. Now, the big difference with this algorithm is that it shuffles things along. It doesn't do swaps all of the time. It just shuffles things along. So our sorted portion now is here, and the unsorted portion is here. When this guy is examined, that goes off to the temp box. The calculation is done. We realize that it's greater than 5, so we don't need to do anything. The sorted portion is now everything along there, and the unsorted portion is everything along there. So this guy now goes off to the temp. Now this is where you can see the big difference. A comparison is done, and 6 is greater than 2. So if I just move it over here. Now where was I? 6 is greater than 2. So 6 is then moved into this slot here, where our 2 came from. And then another comparison is made to this guy here. Well, 2 is less than that. So this guy here then moves to this position. So we end up with 4. Then another comparison is made to this guy, and we can see that this is a greater than 2, so our list then looks like this. We've reached the end, so this 2 here is then inserted into this position, and we have 2. So that swap, the swap for the 2, didn't actually occur until we got to this position here. All the other times, these values were just shuffled along 1. The reason why this happens is because shifting is about 1/3 of the cost of a swap. So that improves the algorithm a little. However, its performance for worst case scenarios is still n squared, which for large amounts of data is still not very good. The number of passes is similar to the others, or it's the same as the others, n-1, because the list is getting shorter each time that we're examining, because some parts of it are ended up into the sorted portion. This bit moves along 1 each time. And the swaps in the worst case scenario is still going to be n-1. So that's 1 swap potentially per pass.
If you liked this video, give it a thumbs up and try out one of my other videos.